Hi everybody, let's talk about the Collatz-Conjecture and how to prove it. If you do not know the problem, there is a link to a list of videos on the topic in the description. Stay tuned. Some days ago I was in contact with Eric Rosendahl on the 3n+1 problem. When I told him that I did a retro-analysis, he responded with a quote from a math student. Why not trying something completely new? How about going backwards from 1? Surely no one has tried that yet. Spoiler, everyone has tried that. Well, so let's summarize the results. Odd numbers n mod 3 equals 0 appear only as odd start values of sequences. Based on the remainder of odd numbers divided by 3, possible odd pre-values of n can be calculated. If you multiply any odd number n with 4 and add 1, you get a new number, leading to the same odd number like n, with 2 more halvings iterations than n. Let's call it an alias, because it replaces n and x instead of n. Everybody tried, everybody could know, but did anybody think about the consequences? Let's take a list of ups and downs. O stands for down, 1 stands for up. This means that any operation for n plus 1 with odd numbers extends the up-down sequence of n on the left side with 1 00 replacing the leading 1. This applies to every sequence with an odd start value. You can extend this alias concept. If you multiply an odd number n by 4 to the k and add 4 to the k minus 1 divided by 3, you get an alias that takes 2k longer to reach the next odd number of n plus the iterations of n. You can easily explain this by a binary chain reaction. And you can easily prove this. You might say, well, but what about m? Okay, the result will be an even number, but if the even number is only divisible by 2 ones, m prime will be bigger than m. Look at this iteration with the start value 27 and its alias 6997. Both lead to 41. And this is definitely larger than 27. Okay, let's have a look at even more strange values like 255 and 127, but let's use the binary system. And here the general iteration with n equals m multiplied by 2 to the k minus 1. And did you recognize that we made a logical fallacy? We forget about the inner m. We iterated with part 2 to the k minus 1 while we forgetting to divide by 2 to the k minus 1. Now we have shown two things. Any odd start value can have an alternative odd start value higher than the largest value within the 3n+1 sequence. Any odd start value which let the following odd value grow has an inner value which decreases while the 2 to the k part is replaced by 3 to the k. This explains the phenomenon of exponential growth within some sequences. And just a side note, 2 to the k minus 1 multiplied by 2 to the k plus 1 equals to 4 to the k. Thus, the next step is to take a closer look at the 3n+1 function. The red method shows that we always add n mod 4 equals 3. And the blue method shows that we can also write n plus half of n plus 1. Wow! What an insight! Everyone knows about it. There's a logic to add odd numbers with different mod 4. As we have seen at the blue method, we add always an odd number mod 4 equals 3. Thus, only 2 of the 3 cases are possible. But you can also write n plus half of n plus 1. It's a blue method, and you can build an addition table. We have on the left-hand column odd n in blue. On the top row, what is added half of n plus 1 in orange. And the diagonal line in yellow contains the result of the operation 3n plus 1 half. Okay, nice. But what's the benefit? Well, we can add the results of mod 4. Now we see next to the blue column which mod 4 leads to which further decrease of the 3n plus 1 result. If the yellow result is 3, the next value will be bigger. If the yellow result is 0 or 2, the next value will be lower. If the yellow result is 1, the next value will be lower, but you cannot determine by how much. It's better to use mod 8 to differentiate between alias values and normal mod 4 equals 1 values. In case mod 8 is equal to 5, we have an alias. If we take mod 3, we can see if there is a pre-value of an odd number. And if we change the starting of the table from 1 to -1, we have the result from the 3n minus 1 function. We can also see how the function behaves when we use mod 2, mod 3, mod 4 or mod 8. I mean the 3n minus 1 function. And here are the formulas of both functions. Actually, nothing very interesting after all we've heard up to now. And finally, we can build another table from which we receive additional information. Just in case you cannot read the table, the blue row contains our starting values. The gray rows contain our respective aliases. The green rows contain pre-values if possible. The orange row contains the value to be added. The yellow row contains the gross result. The light red row contains the net result after all possible halvings. Red numbers are divisible by 3. The last column contains the interval showing how values in the respective row change from column to column. Well, now you have all the necessary tools to write a proof of the Collatz-Conjecture. Actually, it should be easy. At least we are going to rescue Schrödinger's cat. We learned that there is a connection of both functions, so that we can write 3n plus minus 1 to the power of k. If k is even, we have the 3n plus 1 function. If k is odd, we have the 3n minus 1 function. But k cannot be odd and even at the same time. However, we can calculate the result of both functions together. If we understand time as an amount of iterations, I mean how long it takes to have a loop or a diverge in recursive functions, and if we consider -1 to the power of an odd or even number as one value, we can conceptualize Schrödinger's cat and the wave-particle duality. Anyway, that is my interpretation and I like it, just for your information. By the way, I haven't tackled the question which number of 3n minus 1 leads to which cycle. Any ideas out there? Perhaps the prime factors of the starting value, if it is divisible by 3? Thanks for watching.